Hey everyone, welcome back to the channel where we break down maths questions the easy way. Today we're tackling two sine graph questions, one on matching equations to graphs and one on using symmetry to find sine values quickly. For our first question, we can see we've been given 6 graphs and 6 equations, and our job is to match each equation to its correct graph. Let's start by looking at each equation one by one. The first equation we're given is y is equal to 2 sine x. This means we've taken the normal graph and we've times it by 2. Because the number 2 is on the outside, this means that our peaks, our y values, will be double the original graph. Now let's take a look. In our original graph, the peaks are at 1 and minus 1. Because we're timesing the y values by 2, this means our new peaks will be 2 and minus 2. As this is the only change to the equation compared to our original equation of y equals sine x, this is the only change we're looking out for. And we can call this new equation C, as the graph of this is the only one that matches. Our next equation is y equals minus sine x. This means that what values that were previously positive are now negative, and vice versa, as we have reflected in the x-axis. This means if originally a value was at 1, the new value is at minus 1, and vice versa. Once again, this is the only change that has taken place, and so we can now try and match the equation to the new graph. If we take a look, we can see that graph D is the only one which has been flipped, but nothing else has been added or subtracted to it, as graph E, whilst it has been flipped, has also been doubled. This means that the graph matching the second equation is graph D. Our third equation is y equals sine 2x. Now, notice that the 2 this time is inside the sine function, rather than outside. If you've watched my graph transformation video, you'll know that if there's a 2 on the inside, this means that all of our x coordinates halve. Yes, it is a bit counterintuitive. But we're looking for a graph where all of the x values have halved, but the height of the graph, the amplitude, is still the same. Taking a look at the remaining graphs, we can see that graph A is the only one that satisfies this new condition. So the third graph must be A. Right, the fourth equation is y equals sine x plus 2. This means, because the 2 is outside, this means we've shifted the entire graph up by 2 units. Taking a look, the only graph that has been shifted up, so it starts at 2 and its peaks will be at 3 and 1, is graph F. So our fourth equation is F. Now our fifth equation is y equals sine of 1/2 x. Again, if you've watched my video, you'll know that a half x means that all of our x coordinates double. Again, slightly counterintuitive. This means that if one complete cycle was between 0 and 360 this time, only half a complete cycle will be between 0 and 360. If we take a look, only graph B satisfies this, and so our fifth equation maps to graph B. Finally, our last equation is y equals minus 2 sine x. Now, a few of you would have gathered from process of elimination that the answer to this question is E, but let me talk you through why. To start off with, there's a 2 in front of the sine x. This means that, like graph C, the peaks have been doubled from 1 to 2 and from minus 1 to minus 2. However, there's also a minus sign, which means, much like graph D, the graph has been flipped upside down or along the x-axis. Graph E is the only one that satisfies both these conditions, and so we can assign the last graph equation to graph E. And that's how we'd go through the first question. We've managed to map all 6 graphs to their given equation in the table and bagged those 4 marks in the process. Let's now take a look at the second question. We're given a curve y equals sine x between 0 and 360. And we know that sine 30 equals 1/2. Let's use symmetry of the sine curve to find 2 other values. Part 1 asks us to find what sine 150 is. Note that 150 is the same as 180 minus 30. And so we can map along our graph a sort of where 30 is and where 150 then lies, as it's 180 minus that. Notice that this gives us the same value. And so sine of 150 is also 1/2. Another way of looking at it is that it's in the second quadrant where sine is positive. It has the same sine value as 30 degrees, and so sine 150 is 1/2. The second one asks us to find sine 330. Again, by a similar method, 360 minus 30 is equal to 330. This means if we take our value for 360 and we map along 30, we get sine of 330. Notice where sine of 30 was positive, sine of 330 is the same value but negative. And so sine of 330 is minus 1/2. Using a sine graph to visualize is a great way of checking whether the sign in front of your number, so positive or negative, is correct, as if the graph is negative, your answer must be negative as well. And there we have it. That's our second question answered as well. The key takeaway from this is to know your sine graph shape and the amplitudes, reflections, stretches and symmetry to find exact values. If this helped you feel more comfortable about sine graphs, hit like, subscribe for more walkthroughs and drop a comment below if there's a topic you'd like for me to cover next. And if you'd like more information on graph transformations, do check out my previous video. You've got this. See you in the next video.